In the previous examples, we were doing one-step problems, which means that we were always either staying within one phase, like starting as a liquid and then ending as a warmer liquid, or starting as a hot gas and ending as a slightly cooler gas, or we were just experiencing a phase change. So either a liquid going to a gas or vice versa, or a solid going to a liquid and vice versa. But now we're going to extend that a little bit. We're going to push those boundaries. So now we're going to do some problems where we're going to have multiple steps. So maybe, and this would be the extreme version, but maybe we start as a solid somewhere below the melting point. Remember, this is for water. And maybe we're going to end as a gas way the heck up here, okay, above the boiling point. The hardest part about these problems isn't the math itself, it's just making sure that you stay organized and you know which constants you're using where or which standards. So if I were to do this problem, if I were to take, say, a 40-gram piece of ice at negative, 30 degrees Celsius, and then heat up those 40 grams of ice until it's a gas at 130 degrees Celsius, well, how many different equations would I need to use? Well, same answer would be to the question of how many steps are between my two fingers, or how many different equations are between my two fingers, and that would be 5. I would have to heat up the solid, and then I would have to melt the solid. So heating up the solid would be a delta TC problem, and then melting the solid would be a delta H of fusion, and then I'd have to heat up that liquid, so delta TCl, and then I'd have to boil that liquid, so delta H vap, and then I'd have to heat up that gas, delta TCg. I would take those 5 individual equations, I'd solve them, and I'd take their answers and I'd add them together. And that would be my final answer. Now, I'm not going to do a 5-step equation quite yet, but it's no more difficult than a 1-step equation or even a 2-step equation. It's just multiple problems, adding them all up. It's just more cumbersome. Okay, so let's do an example. So here we have a 15-gram sample of water. So we've got 15 grams, there's a mass at 39 degrees Celsius. So there's my initial temperature. It's heated until it is boiled away into a gas. I'm not given a final temperature, but I'm told that it's going to end as a gas. And then how much energy does this require? So I always advise having your energy diagram right here. So we are starting at 39 degrees Celsius. So I don't know, there-ish, doesn't really matter. All right. And I'm going to end as a gas. It doesn't give me a final temperature. So I'm just going to assume that I just have achieved making my water fully gaseous. So it's going to be at 100 degrees Celsius right here, but that temperature won't matter at the end of that step. So if I look at where my fingers are, this is where I'm starting, this is where I'm ending, how many steps are between my two fingers? And the answer would be 2. Okay, I have to heat up my water. I will use Q equals M delta TCl to do that. Now once I've heated that water, I then have to boil that water, and that would require delta H of vaporization. So I'm going to take those 2 equations, solve those for those 2 answers, and add them together. Okay, so that's how I'm going to approach this problem. So first, in fact, I'm going to do this. So Q total is going to be we could even write it like this, Q1, just to make it make sense, Q1 plus Q2. All right, my 2 steps. So Q1 is going to be when I heat the liquid. Q2 is going to be when I boil the liquid. So heating the liquid, that's going to be M delta TCl. Boiling the liquid is going to be M delta H, vaporization. So again, my Q total is going to be M delta TCl plus, so it's heating it up, and then plus M delta H of vaporization. Okay, so let's start with this piece right here. My mass is 15 grams. Delta T, I'm not given a final temperature. I'm given an initial temperature, and then I'm told that it's going to boil. So that means I have to hit 100 degrees Celsius. Okay, so remember, delta T is TF minus TI, so that's going to be 100 degrees Celsius minus 39 degrees Celsius. Now, side note, this number right here does not have significant figures because that's not given in the problem, which means it wasn't measured, which means it's more of a fact than a measurement. This one, however, does have significant figures. Okay, so M delta T C, and then I know I need to use CL. So I'm going to check my specific heat data right here. CL for water is 4.18 joules per gram degree Celsius. 4.18 joules over grams. Did you see what I did there? I fixed it. I'm actually pretty proud of that. Grams degree Celsius. Okay. Let's check my units. So degree Celsius minus degree Celsius is just degree Celsius divided by degree Celsius. That all goes away. And then grams goes away. I'll be left with joules, which is excellent. But now I still have to add this portion right here. So I just did the M delta T CL part. I just heated up the liquid. Right now I need to boil the liquid. So that's going to be an added portion of energy. So my mass is still 15 grams. All right, M right there. And now I need delta H of vaporization. How do I know it was vaporization? Because I already figured it out on my graph. I know I'm going to use delta H vap, not delta H fusion. Okay, that's why this comes in so much handy. That didn't make sense. That's fine though. So here we go. Delta H vaporization, 2,260 joules per gram. That's a lot of energy. 2,260 joules per gram. Okay. No temperature component because, of course, it's a phase change, and temperature remains constant. Grams cancel. Left with joules. Excellent news. Okay. And there is my boiling the liquid. So now just make sure you're paying attention to significant figures. 100 minus 39 is going to be 61, which has 2 sig figs. All right, now I can do all this math, and I'm going to end up with 2 sig figs in this portion right here. So 61 right there times 15.0 times 4.18. It's going to be, with 2 sig figs, 3,800 joules. Now the reason, I normally tell you to save sig figs for the end, and that is true. But we have a different rule here. We've got a multiplying and dividing sig fig rule here and here, and then we'll have to add those 2 numbers, which is a different rule. So I'm going to save that. Okay, so there's my first answer. If you really wanted to, you could factor out the mass and do it that way, but I'm doing it this way for now. And then here we've got 15.0, again, same mass, times 2,260. We do get to keep 3 sig figs this time. That'll be 33,900 joules. Okay, look at how much more energy it takes to boil water than it does to just heat it up. Again, breaking intermolecular forces. We've talked about that lots of times. Now I'm going to add these 2 together. It looks like I get to keep that hundreds place, which is nice. So 33,900 plus 3,800 is going to be, and this is my total or final answer. This is Q total. Is going to be, does that make sense? Yeah, it does. Okay, good. 37,700 joules of energy. Okay, or if you want to, 37.7 kilojoules if you want to be fancy. Okay, and that would be a 2-step Q equation problem.